Bismillahirrahmanirrahim. I am Tabiz Mustafa, roll number ME18041. The topic that we are going to discuss is the asymptotic tracking control of an under-actuated tilt triotor unmanned aerial vehicle. Asymptotic tilt triotor is considered mainly typical as a quadrotor, but it is much more complex and advanced UAV as compared to any quadrotor unmanned aerial vehicle because of having complex drags and thrust calculations. The discussion here relates to nonlinear control of a position of a tilting Type 3 rotor UAV, which is subjected to external disturbances and designs a controller of a positioning subsystem and an attitude subsystem of the tilting Type 3 rotor UAV, aiming at the problem of an inner and outer ring control strategy of the tilting Type 3 rotor UAV. An inner loop outer loop method is used to perform the numerical computations to make precise control and attitude control. And the non-linear moving horizon estimation, commonly known as NMHE method, is designed to realize the optimal estimation of variable parameters and external disturbances. Now, due to its tilt design, it will fly under a great thrust, producing and flies like an Apache helicopter. In UAV, there are two motors that are fixed, but the third one is combined with the tilt servo. And because of its rear servo tilt motor, it stabilizes its speed during the flight and also enables it to perform the operation under the drastic environmental conditions. Now let's discuss some definitions. Robust control is an approach to controller design that explicitly deals with uncertainty. Stability analysis is one of the basic problems in the field of systems control and signal processing. Its goal is to determine the region in the delay parameter space at which the system is still stable. HIL testing is a technique where real signals from a controller are connected to a test system that simulates reality, tricking the controller into thinking it is in the assembled product. Test and design iteration take place as though the real world system is being used. The UAV has 6 degrees of freedom and 4 control inputs, which include the 3 rotational speeds and 1 tilt of a rear servo. It is used in military reconnaissance, investigation of aerial views such as volcanic eruptions. It is also used by the wildlife photographers and also used as fire extinguisher. Now, Usama will elaborate it further. Thank you.
Hello, I'm Assalamu alaikum. I am ME18028. I tried to explain the slides from 6 to 10. The basic working of a tilt triotor has been explained by my project mate ME18040. Now I'll try to cover some important parameters which are necessary for the stable working of a tilt triotor. By the term hybrid control, we mean that how the system robust is, in other words, the efficiency of our triotor. But it is only restricted to numerical simulations only. In order to have a better understanding of numerical simulation, we first need to have some basic knowledge regarding the parameters which contribute to the stability of system or the instability. The first parameter is power required to maintain a stable flight. By this we mean the minimum power required to maintain a stable flight and for the necessary functions of our system. In our case, the necessary power is provided via external dye batteries. The precaution which needs our attention is the viable selection of the batteries. The batteries should not weigh too much, as weight is another important parameter in our designing and numerical simulations. Now I'll move on to the next slide. The first point here is the thrust force. In order to explain a triotor, I'll relate our triotor to an helicopter or an APEC helicopter. In an APEC helicopter or any normal flying machine, there are four forces acting on it: drag, lift, thrust, weight. Drag is a horizontal force exerted on a helicopter which restricts the forward motion of a helicopter. Drag is generally due to the air resistance. In order to overcome the drag, engines provide the thrust. When the thrust is more than the drag, our helicopter will move forward. This is also called forward driving force. The third force is the weight of the helicopter, which acts vertically downward. The fourth and the last force is the lift, which acts vertically upwards. This force appears when the helicopter blade sucks the air from the surrounding and throws downward. And due to Newton's third law, an equal and opposite force is produced. This force is referred to lift. In order to move our triotor forward and upward simultaneously, one out of three blades is mounted slantly, that means at an angle relative to the blades. Hence, the force components of this blades incorporates to forward as well as upward motion of our triotors simultaneously. In the slide number 7 and 8, mathematical form of my previously explained parameters are given. That is thrust force, propeller's torque coefficient, thrust coefficient, lift force, thrust coefficient, lift force, drag force, and coefficient of drag. Now I'll move on to slide number 9. The first point here is control law design. A system is said to be control law design when it comes back to its equilibrium when the time varies. In order to understand this, I like to quote the example of a takeoff of a passenger plane and a fighter jet. They both take off under different conditions as they are designed under different conditions of control law design. The next auxiliary control input vector and reference altitude trajectory are mathematically explained, which are briefly explained in the reports. Now I'll move on to the slide number 10. The first part is the dynamic model of the position subsystem. In this part, the important parameters in the designing of the lift triotor has been represented in the state space. The important point here to notice here is the fact that we neglected the unstable parameters which are going to incorporate to the instability of the system. The next point here is the filtered tracking error. Filtered error can be of various types depending on the nature, that is mechanical, electrical, etc. They affect the robustness of the system. The last point here is the auxiliary error signal. It helps to understand the input and output observation of the system. Thank you. The remaining slides will be covered by my project mate ME18026.
Bismillahirrahmanirrahim. My name is Muhammad Hassan and my roll number is ME18026. We have discussed the mathematical model as well as this final state space representation of our system. The concept of the state space was given by the Euclidean. Now we will discuss the stability analysis, which will lead us to propose some of the physical model as well. Here we have slide number 11. Here we have asymptotically stable equilibrium for the dynamic system. Basically, we have some of our choices as well. We can make the system stable or we can make the system asymptotically stable. Both will converge at the equilibrium point. But there is a big difference. An equilibrium point is said to be stable if for some initial value close to the equilibrium point, the solution will eventually stay close. It will not all the time remain on the equilibrium point, but it will eventually stay close to the equilibrium point. Or an equilibrium point is said to be asymptotically stable if for some initial value close to the equilibrium point, the solution will always try to converge on the equilibrium point. Hence we can say that for an asymptotically stable equilibrium, we will have greater stability. We will have greater chances of our flight to be controlled by our mathematical parameters, by our parametric state variables. We will choose some of the variables which will lead us to the stability. There is partial state feedback law, partial state. Basically, these two terms are related with the mathematical. You can say that this is partial integration, such that the equilibrium state points here, but we have we made our system asymptotically stable equilibrium, which will give the value of zeta is equals to 1, and we want our system to be critically damped, as we have discussed already that damping is necessary. So for being a stable system, we will choose critically damping. Uh, uh, as we have already discussed in our academics, BIBO stability, and this system is BIBO stable. A time variation system or a time invariant system is asymptotically stable if all the eigenvalues of the system matrix have negative real parts. If a system is asymptotically stable, it is also called as BIBO stable, bounded input, bounded output. In machine control system or control theory, bounded input, bounded output stability is a form of stability for linear signals. This is a condition that linear signals must be present, and systems that take inputs, we can't form such a system which will not run according to our desired values. We always try to achieve some of the system that will work according to our desired values. So if a system is BIBO stable, then the output will be bounded for every input to the system that is bounded. This is what we wanted. In control engineering, a state space representation, as we have discussed, I am discussing this state space representation because it have directly impact over the stability analysis. Here we have simulations and results, which and the graph is between the time and angles. These are the angles at different rotors, and this and here we have used the subscript d. This is the desired, and the angles which have nothing in under the subscript are the actual. They are, they are converging on the same points, means they are relatively close. They are they are staying close to the equilibrium point. This is what asymptotically stable means. These graphical results helps in understanding this, that the state of system we predicted for our model is going very effectively. And we can see that there are some amount of overshoots, but they are negligible. They are very least in number. They are very lesser in number. If there will be lesser air resistance, then these overshoots will also reduce, and we will achieve minor amounts of overshoots. Uh, uh, we want our system to be critically damped. Critically damping is when the system returns to its equilibrium position in the shortest possible time without any oscillation. This is what we want our system to give us the desired result. If we control our, for example, this is a triotor. If we control our triotor, if we want our triotor to be take a bank left at left side, so I want that it will come on its equilibrium line of flight very effectively. This will only be possible if we design our system as critically damping and asymptotically stable equilibrium. Let's move on to the next slide. Here we have another stability analysis, and this is again between the time and the angles. Hence we can clearly see that the lines are converging. As the stability here, again we have maximum. It can be seen clearly that control law design that we use to predict the direction of our unmanned aerial vehicle, making the system coming back to its stable state very effectively. If we didn't use, or if we neglected the control law design, then we have some of the mathematical difficulties as well we have some of the designing difficulties as well. Hence our system is working according to our desired values. Hence we can say that this is in equilibrium position as well. According to the stability analysis, this is what we wanted. Hope it works for our proposed model as well. After seeing some of the calculations from various sources and after researching a lot, we have proposed a, you can say that a pretty much slice of our drone. This is what we propose. Here we have maximum amount of curves on the front side. This will neglect some of the drag resistances, air resistances, which which tilt its angle easily and can uh, cruise at a speed at our desired speeds. Let's move on to the next slide. Here we have orthographic views of our proposed structural model. As we can here we have here in this picture, there we can see that the curve is elliptical curves, and this is the front side. The air will move from this and will go from this, so this will remove some of the drag resistances as well. This is the basic and the most important things in the mathematical as well as the physical structural modeling of for any system, for any aerial vehicle, whether it is manned or unmanned. Here we have written that as the values of the velocity increases, the thrust increases and the radial axis force tends to increase, and it will become much easier to get lifted up, which is possible by the heavy propellers design and synchronous motors. This is one of the important aspect. Here we have another one that hence we can easily predict that control system scenarios are only possible under stable conditions. We design our system to be asymptotically stable under critical damping, and we are achieving our desired parameters greatly. This is a conclusion. Here we have written that for the robust design manufacturing, it is necessary to have a stabilized system as well as the parametrically controlled state variables, the equations which is designed for calculating the state variables and for solving the matrices on MATLAB simulation must necessarily have all the parameters which are causing resistances against the applied ones. Basically, this means that we have to include all the parameters, not the stable ones, uh, uh, but we have to include all the parameters which are taking place in our system. For from this we can design a proposed model. This project was a great opportunity for us to learn. We have cleared some of our basic concepts in the aerial technology. The world is moving so fast in this technology. Hope it will work for us in the future as well and for predicting some of the models as well. Thank you.